Let's talk about stopping distances, forces and braking in general. Some of the things we're going to cover in this video will be what thinking distance and braking distance is, and then we'll talk about stopping distance, we'll talk about reaction time, we'll talk about the factors that affect reaction time and thinking distance. We'll also talk about the factors that affect the braking distance and how we can estimate decelerating forces. So this is going to be an all-in-one video, so please make sure you stick around till the very end. So what exactly is stopping distance? Let's say you have a car now and you're driving on a highway. The time it takes, or let's say the distance you cover between the time you saw the emergency, probably a dog crossing the road or just an emergency of a kind, or someone driving recklessly and you needed to stop. So the distance your car covers from the time when you saw that emergency and the time your car came to a final stop is the stopping distance. And yes, from that definition, we can always divide it into two. You have the thinking distance, and then we have the braking distance. If you're to split that now, let's say you see you're driving and then you saw like a baby, like a kid or a puppy crossing the road, and you're like, oh snap, I need to match my brakes. So from the time you thought in your mind that I've got to stop, and then you placed your foot on the pedal, that time, yeah, it could be milliseconds. That time between when you thought about it and when your foot hits the pedal is what we call the reaction time, one. And then the distance covered by your car during that time is what we call thinking distance. And the journey doesn't stop there. By the time you put your foot on the pedal and you match your brakes, the distance your car covers from that time to when the car comes to a final stop is your braking distance. So basically, stopping distance is thinking distance plus braking distance. So this is basically what we talked about on the previous slide. You saw an obstacle, the time it takes you to see the obstacle and then react to put your foot on the pedal is a thinking distance. The time it takes for the brakes to be applied fully and it comes to a complete stop is your braking distance. For example, it says at a speed of 20 meters per second, a vehicle had a stopping distance of 40 meters. The car traveled 14 meters whilst the driver was reacting. What was the braking distance? Basically, in physics kind of problem, you write out your variables. So you have your stopping distance, you have that's 40, you have your thinking distance, that's 14, and then the question says we should get the braking distance. Just plug in that equation, stopping equals thinking plus braking. Make braking distance the subject, you would have 40 minus 14, that gives you 26 meters. Let's talk about the relationship between these guys. You're moving at a constant speed of, let's say, 20 miles per hour, which is also equal to 32 kilometers per hour if you're working with that. But let's just take 2 miles per hour at this point. You're moving at 20 miles per hour and your thinking distance, your average thinking distance is about 6 meters. Your braking distance is also about 6 meters as well. That makes your stopping distance 12. If we double the speed from 20 to 40 miles per hour, your thinking distance, which was initially 6, will increase to 12 meters. Your braking distance, which was initially 6, will increase to 24 meters. You see the relationship there? When you double the speed, the thinking distance doubles, the braking distance quadruples, And then your stopping distance triples. So your stopping distance goes from 12 to 36. And then you can walk your way through different scenarios like that. So how do we measure reaction time? A measure of how much time passes between seeing something and reacting to it is called the reaction time. Now, the human reaction time for someone who is alert, we mean someone to see something, to react to something that is happening. The human reaction time for someone who is alert, it could be someone waiting for something to happen. It could be an athlete waiting for the start of a race. The reaction time is usually within the range of 0.2 to 0.9 seconds. It varies, but it's usually within that time. But how do we measure it? The human reaction time, very simple. You have two persons hold a ruler. The first person holds it at the 0 mark, or the first person could hold it at the 30 cm mark, and then the second person at the 0 mark, or you could flip it. Now, the second person holding it underneath like this. This is person A, this is person B. So the second person will not hold the ruler tightly. No, he will just leave some space. So he's not holding the ruler, but his hands, his fingers, they're all over the ruler. But person A is holding it tightly. And then you have the third person with a timer. Once person A drops the ruler without prior information, the timer is started at the same time. Okay, you also have person A start the timer with the other hand at the same time. So he drops the ruler, or she drops the ruler without prior information, and then person B has to catch it. So the time it takes for person B to catch that ruler is the reaction time. And then, since it's a ruler, we can obviously measure that distance multiplied by the reaction time to get the speed. Or the other way around, the speed multiplied by the reaction time to get the thinking distance. That's your typical, velocity equals distance over time. Remember, we gave a range for the reaction time, or the thinking distance in this case. And we said it varies from person to person. Why? Because there are a couple of factors that affects that. Number one, tiredness. Now you notice that when you're tired, your enthusiasm, your level of alertness will drop. And this is not just the case for drivers, just generally for human beings. When you're tired, you will have slower reaction times. That's one. Two, when you're distracted, you're driving and then you're funding with your mobile phone while driving, you'd have slower reaction times. It would take some time before you're able to react to an emergency and decide to match your brakes, which most cases will be too late and that result in an accident. Three, you have intoxication. Don't drink while driving. Don't drive while drinking. So consuming a lot of alcohols and drugs as well. Drugs is also one of the real issues of accidents, because the person's judgment will be affected, which in turn will affect the person's reaction time. And then, we've had a couple of people in the past that got into an accident because they were drunk. The reaction time was pretty slow. And then those kind of people, they will not only affect themselves, they would also affect other people, other road users. So we have to be very careful about that. Speed is another factor. The faster you're moving, the slower your reaction time. If you're moving on the highway pretty fast, you find it really difficult. Now, maybe not really difficult, but then your reaction time will be pretty slow, and your car would have covered a much larger thinking distance. And like I said earlier, which might be too late. So thinking distance is directly proportional to speed. And we can show that on a straight line graph passing through the origin. As the thinking distance doubles, the speed also doubles, or vice versa. Double the speed, double the thinking distance. And for braking distance, we've explained what braking distance is. You can always go back and then watch that again. The factors that affects braking distance, you have the vehicle speed. We've talked about that the faster you move in, the longer the braking distance that you will require. Your car will cover a longer distance before it comes to a stop. Vehicle condition. If your vehicle is not roadworthy, if your tires are worn out, if your brakes are bad, and then you go on the road with that car, then you endanger yourself. Apart from the basic issue of increasing your braking distance, you'd also endanger other people because your car is obviously faulty. So let's always maintain our cars, right? And then we have road conditions. Wet and icy roads reduce friction because it will be a lot slippery, and we don't want that kind of situation. And that's one of the reasons why you see during the winter the government or companies in charge of de-icing will try to de-ice the roads to make sure that you do not have ice on it, because your car can easily skid off, and then when you apply your brakes will be less effective. And then finally we have the vehicle mass, right? So the bigger the vehicle, let's say a lorry or a truck, the longer the braking distance. So a car or a bike will have a shorter braking distance because the mass is small, and then a much bigger one like a lorry or a truck will cover much more distances before they finally comes to a stop. So braking distance is proportional to speed squared. That means if your speed doubles, your braking distance will quadruple. Get that arrangement. For thinking distance, if your speed doubles, your thinking distance doubles. If your speed doubles, your braking distance will quadruple. And yes, what is the relationship between energy transfer during braking and braking? So what simply happens is that when you match your brakes, initially before that time, your car has a certain level of kinetic energy. And that energy will be converted into thermal energy. That conversion, we can quantify that as work done by brakes. So the work done by the brakes is equal to the kinetic energy lost as thermal. And then your brakes will dissipate that thermal energy into the surroundings. So friction between brakes and wheels converts kinetic energy into thermal energy. And yes, we have graphs for quantifying stopping distances. Now, from your knowledge of velocity time graphs, you know the area under the graph is your total distance. So the later part of the journey that will be given to you in your exams, the thinking distance is usually like a rectangle or sometimes a square, which is what you have on the screen, because at that time you reacted that you needed to match your brakes. So at that time the car is moving at a constant velocity, so you slam your brakes. You can quickly do that, the calculation, by just doing your length times breadth and get the area, which is your thinking distance. And then for the braking distance, which is usually like a triangle, a right angle triangle in a way, because it shows the graph sloping downwards, which shows you obviously decelerating. You can do your half base times height and then get your braking distance. Addition of the two will give you the stopping distance. And finally, work done by brakes equals half mass velocity squared, which is your kinetic energy lost. All right, so force times distance equals kinetic energy equals work done. And you can always flip that around. So it's more like saying A equals B equals C. So you can equate force times distance equals kinetic energy. You can equate work done equals kinetic energy and all of that. So the final calculation you have on the screen, we need to get the braking force. We have the variables, our car mass, our speed, our braking distance. To get the braking force, we just do the kinetic energy. That gives us 243,000 joules. And then the braking force, that is work done divided by distance. Your work done is 243,000 joules divided by the braking distance. You get 10,125 newtons. So, safety tips. Don't drive when you're tired, avoid distractions, never drink and drive, and then try to maintain your vehicle. So, that'll be all, and I'll see you in the next video.